Welcome to Crypto 101, a first principles jargon-free course on blockchain and its impact on financial services. We are in the process of learning how cryptocurrencies mimic the properties of fiat money. In this lesson, we will conclude our discussion on the property of account security. Specifically, we will learn how digital signatures are generated and verified. We are currently learning the method by which cryptocurrencies mimic the second of the four properties of fiat money, namely account security. In the previous two lessons, we laid the groundwork for understanding digital signatures. In this lesson, we will cover digital signatures in detail. Before we delve into the mechanics of digital signatures, let us recap some relevant learnings from previous lessons. A payment message along with a digital signature can be created in an offline mode. This digital signature is analogous, though not identical to, the wet signature on a paper check. When the payment message is broadcast to the blockchain network, its digital signature must be validated before transfer of value between payer and beneficiary can occur. Software running on the computers within the blockchain network verify the digital signatures of the transactions being submitted by the payers. The work done by the operators of these computers is analogous to, though not identical to, the work done by bank employees in verifying wet signatures on a check. Alice wishes to make a payment to Bob. She creates a payment message that has a digital signature attached to it. A software program generates the digital signature by applying some mathematical logic. While the details of the mathematics are out of our scope, we will develop a foundational understanding of what occurs. Conceptually, we can think of the digital signature as a combination of two elements. One element is a stamp of authority. This is the private key. Second element is the payment message on which the stamp of authority is being affixed. The private key thus represents who is signing, while the payment message represents what is being signed. While conceptually the digital signature consists of two categories, there are actually three numbers that go into the creation of a digital signature. The first number is the private key. We will denote it with a small k. The second number is a random number that we will denote as r. The third number is a numeric representation of the payment message, that we can denote as m. The digital signature is applied by applying mathematics to k, r and m. Next, we will look at what these three numbers are. By now, we are familiar with the first number, small k, which represents the private key. It is a random number generated at the time of Bitcoin account creation. It lies between 1 and a very large number. The second number that goes into the digital signature is a random number, denoted by small r. While the private key is also a random number, this random number is generated every time a payment message needs to be signed. In contrast, the private key is only generated at the time of Bitcoin account creation. Next, we will learn how small r is generated. Before we learn how the random number is generated, let us recap our learnings on the public key generation. In the previous lesson, we learnt that there is a class of XY graphs known as elliptic curves. The public key is the x-coordinate of a point on this curve. Next, we will refresh our memories on how the public key was generated. There is a generator point, G, on the version of the elliptical curve that Bitcoin uses. G is the same for everyone. It is like the train station from which every train departs. A random number, which we called the private key and symbolized by small k, was generated outside this graph. Depending on the value of small k, a point on the curve was chosen. The x-coordinate of that point was the public key. We denoted the number by big K. We also learnt that the distance between G and big K is dependent on the value of the small k. Since the same private key will not be generated twice, no two people will have the same private key and hence, they cannot have the same public key either. For the purpose of digital signature generation, the same process is repeated. A random number is generated outside the graph and depending on what this number is, a position on the elliptic curve is chosen. We can denote the x-coordinate of that position as small r. Small k and big K remain the same at the account level but the r changes for every new payment. The third number which goes into the digital signature is a numeric representation of the payment message. The payment message contains details of the intended payment. It includes details like the amount and the destination blockchain address. These details need to be converted to a number. Next, we will see how this is achieved. The conversion of the payment message to a number is achieved by a hash function. We had encountered an example of a hash function in a previous lesson. The purpose of the hash function is to convert the payment details to a fixed length numeric output. We can symbolize the hash of the payment message to be small m. In a previous lesson, we had demonstrated how the hash function converts an arbitrary length input to a numeric output. Let me do another demonstration. The hash function that I am demonstrating on this website is not the same as the one Bitcoin uses, but the concept is exactly the same. I can take a paragraph, which is the preamble of the US Constitution, and hash it. The hash is a unique number that you can see at the bottom. Even though the hash output is a number, its visual representation is alphanumeric for conciseness. Finally, remember the concept of unique input-output pairs from the previous lesson? No other paragraph can result in this hash output. At this point we have three numbers. First, we have the private key. Second, we have a random number specific to the intended payment. Third, we have the hash of the payment message. As a final step, a mathematical function is applied to the three. The output of this function can be denoted by small s. The digital signature attached to the payment message is a pair of two numbers. One number is R, which is the random number that was generated as part of the signature creation. The second is S, which was derived by applying math to the private key, the random number, R, and the hash of the payment message. Below is what a digital signature attached to a payment looks like. Even though the visual representation is alphanumeric for conciseness, these are actually numbers. As we can see, while this signature is analogous to the wet signature on a check, it looks very different. At this point, we can pause and reflect on an observation I made in the previous lesson. Bitcoin security leverages a bunch of numbers. These include the private key, the public key, and the Bitcoin address. We can now add a fourth to this list, the digital signature, which itself is a pair of two numbers. These numbers are products of mathematical functions, and by themselves, they are purpose neutral. However, they are being used for very specific purposes within the Bitcoin ecosystem. Let us go back to Alice and Bob. Alice creates a payment message and attaches the digital signature to it. She can do this offline. But if she wants the value of Bitcoin to be transferred to Bob, she must broadcast the payment message to the blockchain network. She broadcasts two pieces of information. The unhashed version of the payment message. The digital signature, which as we learnt is a combination of two numbers, R and S. We can now introduce the character of Mark, who runs a computer on the Bitcoin network and performs the role of a bookkeeper. He must verify the digital signature is correct before the transfer of value from Alice to Bob can occur. Before we move on to digital signature verification, it is helpful to reflect on what is publicly known and what is secret. Let us list everything so far that is publicly known. The public key. The Bitcoin address. The digital signature. The payment message and its hash. Additionally, all the mathematical functions being used are publicly known. The only attribute that is secret and known only by the account holder is the private key. The question Mark needs to answer is: was the digital signature generated by someone who knew the private key to the source Bitcoin address? Since the public key is uniquely linked to the Bitcoin address, this question can be restated as below. Was the digital signature generated by someone who knew the private key corresponding to the public key? The function of the public key is to prove knowledge of private key without revealing it. To verify the digital signature, three pieces of publicly known information needs to be input into the verification software program installed on the Bitcoin nodes. First, the unhashed version of the payment message. If the same payment message is hashed using the same hashing algorithm, the output will always be the same. Hence, the verification software can independently hash the same payment message. The second piece of input is the public key. The final piece of input is the digital signature associated with the payment message. The software can execute the verification based on these three inputs. We can now compare the inputs required for the creation versus verification of the digital signature. The creation of the digital signature requires the raw payment message and the private key. The verification of the digital signature requires the raw payment message, the public key, and the digital signature attached to the payment message. It is almost miraculous that the digital signature can be verified without ever knowing the private key. The mathematics behind this is complex and outside the scope of this course. Hence, we will only summarize the intuition behind it. There is one number, which is an input. This number is the private key. The input is secret. There are two numbers that are outputs. First, is the public key. Second is the digital signature, which itself is a pair of two numbers, R and S. The outputs are publicly known. The mathematics underlying the verification is able to prove that the two outputs derived from the same input, without knowing the value of that input. The mathematics used behind the digital signature generation and verification is called elliptical curve digital signature algorithm, or ECDSA. So far in the course, we have noted that Bitcoin functionality involves execution of multiple mathematical functions. We can list the ones we used so far. Generation of a random number, which is designated as the private key. Elliptical curve multiplication for conversion of private key to public key. Hashing algorithms for the conversion of public key to Bitcoin address. Conversion of large numbers from decimal format to base 58 format. Digital signature creation using hashing algorithm and ECDSA. It is easy to get lost in the math. Hence it's useful to reflect on the purpose this math is serving. The mathematical functions we reviewed replicate two functions that banks do. These functions are the issuance of bank accounts and the provision of an authentication mechanism for accessing the bank accounts. The math that we just reviewed is embedded in two workflows. The first is the account opening workflow by which a new Bitcoin address is acquired. The second is the payment workflow by which a payment is made. Next, let us briefly look at each one of them. The Bitcoin account opening workflow is very simple. An individual requests a Bitcoin address via a software program. 3 numbers are issued to the individual. These are the private key, public key, and the Bitcoin address. Next, we will highlight some notable characteristics of the workflow. The acquisition of a Bitcoin address is self-serve. As long as a software program can generate the 3 numbers, connectivity to the internet is not required for account opening. The underlying mathematics ensure that no 2 people can land up with the same numbers. There is no limit to the number of addresses and associated keys you can generate. In the payment workflow, an individual creates a payment message. A software program generates a digital signature using the private key of the payment initiator. The payment is then submitted to the blockchain network. It is validated by blockchain bookkeepers. Finally, the transfer of value occurs between source blockchain address and the destination address. At this point, it is a legitimate question to ask on what exactly does a person in the account opening and payment workflows do. What we have learned is so far only a theoretical description of the workflow. The unanswered question is, what is the user interface by which the account opening and payments workflow occur? We will cover this in the next lesson. But before we close this lesson, let us conclude with some final reflections on digital signatures. To understand digital signatures better, it is useful to reflect on the similarities and differences between a wet signature on a check and a digital signature. We will begin with the similarities. An obvious similarity between the wet signature on a check and a digital signature is that both are attached to a payment message. The payment message on a check is often a combination of handwritten and printed attributes. The source account number and check numbers are usually printed while beneficiary name and amount are often handwritten. In crypto payments, the payment message is entirely electronic. Another similarity between wet signatures in checks and digital signatures is that they can be executed without being connected to the internet. We can write the payment message on a check and sign it, without being logged into a bank's systems. Similarly, we can create a crypto payment message and digitally sign it with our private key, without being connected to the blockchain network. A major point of difference between wet signatures on a check and digital signatures attached to a crypto payment is that the latter changes with each payment, while a person's wet signature remains the same. Next, we will review an example to understand the significance of this attribute of digital signatures. Imagine Alice writes a check to Bob. The check Alice writes is for $70. She writes the number and amount on the far right on the check. Bob adds a 5 to the left of both the number and the amount and deposits to his bank. This is called an altered check. This reason this can occur in check payments is that the wet signature is the same across all transactions. Next, we will see what happens if this occurred in crypto payments. Let us go back to the scenario where Alice submits a payment message with a digital signature. The intended beneficiary is Bob. Mark, a validator on the blockchain network, changes the destination blockchain address to his own instead of Bob's. Before we proceed further, let us see what actually happens to the transaction that Alice submitted. Mark's computer is a node on the blockchain network. After Mark approves the corrupt transaction, he broadcasts it to nodes that are immediately connected to it. Each of the nodes in turn broadcasts the transaction to the nodes connected to it. Hence, the transaction is broadcast to the entire network in an exponential manner. A majority of the nodes must approve the transaction for it to be valid. Each of the nodes runs a software program that validates transactions. The digital signature that Alice attached to the payment is derived from a combination of the payment message and the private key. Hence, if the payment message is changed, the software program that is validating Alice's transaction would immediately flag that the hash of the message that was used to create the digital signature does not match the hash of the current message. Hence, the transaction will be rejected by other bookkeepers even if Mark approved the corrupted transaction. We are currently learning the method by which cryptocurrencies mimic the second of the 4 properties of fiat money, namely account security. In this lesson, we completed our learnings on account security as maintained in Bitcoin. So far, our discussion of Bitcoin account opening and payments has been at the theoretical level. In the next lesson, We will learn how these workflows play out in real life. But before proceeding to the next lesson, take a couple of minutes to review the summary of this lesson.